Good afternoon. Yesterday we were looking into working with polynomial division, and then we crossed over to working with domain and asymptotes, and we've been looking at vertical asymptotes and just crossed over into the horizontal and slant asymptotes categories. And again, whether we have horizontal or slope asymptotes, if any, is contingent upon how the degree of the numerator in a rational function will compare to the degree in the function's denominator. And again, if the numerator degree is less than what is in the denominator, okay, there will be a horizontal asymptote at y is equal to 0. And if the degrees of the numerator and denominator are the same, we're going to have a horizontal asymptote, which will be y is equal to a non-negligible constant, which will be resulting from taking the ratio of the highest degree terms. And if the numerator has a higher degree than what is in the denominator, okay, by a difference of 1, okay, there's going to be a slant asymptote, and that is going to be a straight line. And if we have the difference between the numerator and denominator to be such that the degree of the numerator is 2 degrees or higher, okay, then there's going to be no horizontal or slope asymptote. And just sort of blending in together what we have had with domain and vertical asymptotes. Let's say that if we were to determine the slope, not the slope, like the slant asymptote is going to be in slope-intercept form, and we might have a slant asymptote. Let's say if we're looking at determining the domain and asymptotes. And we'll say for a rational function, okay, we'll say we'll have r of x is equal to x cubed plus 3x squared plus 4x plus 1 all over x squared plus 1. Okay, now for what we have in the case of the restrictions concerning rational functions, okay, we're going to have that the denominator cannot be 0 in value. Okay, so in this case, x squared plus 1 cannot be 0. Okay, and so we have a little bit of history to repeat, especially in light of what we looked at with the last example yesterday. And for x squared plus 1, again, we have the sum of squares, which we cannot factor into real integer coefficient terms. And if we look at isolating the x squared, okay, so I can just move the 1 over and say we have the x squared cannot be equal to -1. And again, just going from x squared to x, taking what we have in the case of the square root property. Okay, so if we go from x squared to x, we have a -1, we have plus or minus, okay, the square root of -1. And here we have the x cannot be equal to plus or minus I. And if you notice, we have in the mix, okay, the only values we had to be excluded are not even in the real number system. Okay, so in this case, no real values are excluded. And we're not worried about complex numbers. Okay, so if there's nothing from the real number system that is excluded, that means that for the domain, we're going to end up with a set of all real numbers. And furthermore, since no real values are excluded, there's no excluded value that will become a hole in the graph of a function or a vertical asymptote. Okay, so in this case, all right, so we don't have any vertical asymptotes since we don't even have an exclusion from the domain. All right, now because we don't have a vertical asymptote doesn't mean that we're not going to have any asymptote at all. Okay, and the possibility of the existence of an asymptote, this is going to ride upon comparing the degrees of the numerator and denominator. Okay. So looking at the numerator, okay, we had the highest order term in this 4-term set, okay, that is going to be x cubed. Okay, so the degree of the numerator is going to be at 3. And for what we have in the denominator, now the higher order term is x squared, and this is second degree. All right, so you have n is at 3 and m is at 2. And this is going to be a case of where n is greater than m by 1 degree. So we're going to end up with a slant asymptote. And the slant asymptote is going to be a straight line that's going to be derived from the quotient of dividing the numerator by the denominator, okay, of the rational function. And if I could, okay, I would use synthetic division, but because the divisor, namely the denominator, okay, is of second degree as opposed to first degree in x, okay, we had to perform long division. Okay, so we got in this steps I have x squared, and just for placeholder purposes, I'm going to throw in 0x. And for what we have in the dividend, okay, so we have x cubed plus 3x squared plus 4x plus 1, and looking at the long division, so x squared will go to x cubed x times, so the first term of the quotient is going to be at x, and distributing x over x squared plus 1, or x squared plus 0x plus 1, so we have x cubed, and you have plus 0, in this case 0x squared, and x times 1 is at x, and looking at applying subtraction, so x cubes will go out. Okay, now we have 3x squared, okay, minus 0, so we have 3x squared is going to be brought down, and we have 4x minus x, so that is going to be at 3x, and then we have bringing down 1. Okay, so to x squared into x cubed, now we have this trio of terms. Now I can take x squared directly into 3x squared 3 times, and we have with distributing. Okay, so 3 over x squared, we have 3x squared, you're going to have 0 to follow, and 3 times 1 is 3. And applying subtraction once again. Okay, so 3x squared goes out, and we have 3x to be brought down, and we have 1 minus 3, which will be negative 2. Okay, now 3x minus 2, that is going to be the remainder, and I cannot take x squared directly into 3x. So for what we have here, okay, we had the resulting quotient, okay, to be at x plus 3, and that will be the expression that is going to define the slant asymptote. Okay, so in this case, okay, from the quotient, okay, we have x plus 3, and so the slant asymptote is going to be at y is equal to x plus 3. So just going back, okay, again, the domain consists of all real numbers, since there were no real values excluded. Okay, only exclusions were in the complex domain, but again, we're not dealing with complex numbers. And again, since there were no real exclusions, there was no vertical asymptote. And again, from the degree comparison, okay, we had the degree of the numerator to be 1 higher than what is in the denominator. Okay, and so from this we have a slant asymptote, and we have a y is equal to x plus 3. And just looking at the visual layout for this, and we got for this function, okay, I already had this set up, okay, and looking at the rational function itself. Okay, so if I try to zoom in here, okay, so we got for the sort of the red wavy entity, okay, this would be in reference to r of x, and for the slant asymptote, again, we have y is equal to x plus 3, and those to the extreme left and to the extreme right. Okay, we're going to have the graph of the rational function and the slant asymptote to be running pretty much alongside each other. And just kind of a reminder, okay, now with slant and horizontal asymptotes, okay, you can have the graph of the rational function to touch or even intersect, but in the case of the existence of vertical asymptotes, again, the graph of a rational function never touches a vertical asymptote. Again, with extenuating circumstances, you can have contact between a rational function and a horizontal or slope asymptote, but for vertical asymptotes, again, those are off limits. Okay, now another case of what we have concerning domain and asymptotes, and we have in the case of r of x, and so we have is equal to 2x squared minus 18, and say we have all over x squared plus 5x plus 6. Okay. So just looking at the domain to see if we have any restrictions this time around. Okay, so the denominator, we have x squared plus 5x plus 6, which cannot be 0. Okay, and this one is going to have restrictions or exclusions. Since we have this trinomial is factorable into integer coefficients of real terms, and now we have the factors of x plus 3 and x plus 2, and for x plus 3, if this cannot be 0, we have that x cannot be negative 3, and we have with the other factor x plus 2, if this cannot be 0, then we have that x cannot be negative 2. And so we'll have for the domain, okay, so you have negative 3 and negative 2 excluded, and so we have from the lower end, okay, we have those values of x that will be less than negative 3, and we have in between, we have those values of x between but not including negative 3 and -2. And for the rest of the set, we have those values x, which will be greater than -2. Okay, so you have two exclusions from the domain, and we could have potentially up to 2 vertical asymptotes. And if that is not the case, you might have one hole and one vertical asymptote, or if you have the corresponding factors of x plus 3 and x plus 2 to cancel, you might have 2 holes in the graph. And just looking at what we have in the determination of any vertical asymptotes, and we have with the rational function, if I look at factoring, so we have with 2x squared minus 18. Okay, so you have 2 is the greatest common factor. So you have 2 times, okay, the quantity of x squared minus 9. And we have all over, again, from x squared plus 5x plus 6. Again, we have x plus 3 and x plus 2 in the factors. And in the numerator, so just take the factorization out once again. So we have x squared minus 9 with the difference of squares. And that portion, again, we have factoring out to x plus and x minus 3. And looking at what we have over the factored out denominator terms. And so for what we have here, is we have x plus 3 common to the numerator and denominator. So we're going to have x plus 3 to cancel completely. And in the simplified form, and I'm just going to leave in factor terms, so the numerator, okay, we have, you can say 2x minus 6, or 2 times the quantity of x minus 3 all over x plus 2. All right, so for what we have in the mix, okay, so x plus 3 completely cancels. So that means that -3, the corresponding 0, is not going to be a vertical asymptote. So for what we have in consequence, okay, x equals -3, it's going to be a hole. And we have with x plus 2, okay, x plus 2 remains. And since x plus 2 is still around, okay, that means that we're going to have one vertical asymptote. And that's going to be with the 0, whereupon we have x equal to -2. All right. So you at least have one asymptote with the vertical asymptote, x equal to -2. Okay, now for what we have in terms of finding any other asymptote, okay, so again, this comes down to degree comparisons. Okay, so we have in the numerator, okay, the higher order term is 2x squared, and the denominator we have x squared. So we have that n is equal to 2, and that m is equal to 2, and both n and m are the same value. So if n is equal to m, when we have a horizontal asymptote, we're going to have y equal to the constant upon taking the quotient of the higher or highest degree terms in the numerator and denominator. Okay, so about n is equal to m. So you have a horizontal asymptote. Okay, so we're going to have y is equal to 2x squared over x squared. Okay, so we'll have that y is equal to 2. Right. So we got one vertical asymptote, one horizontal asymptote. And just looking at what we have, okay, so you have showing up. Okay, so we got the graph of the rational function. Okay, and this is split up into two sections, and again you have splitting up. Okay, so you got the vertical asymptote at x equal to -2, and again this asymptote is off limits, and we have, again, since x plus 3 canceled out, we will have a hole located at x is equal to -3, and we have included, okay, we have the horizontal asymptote at y is equal to 2, so we have at the extreme left and right, you're going to have the sections of the rational function, okay, to run tangentially to that particular line. Okay, so this will be the general image of what we have in this one. Okay, so for the key features, you got the asymptotes, and again we have the hole located at -3. Okay, now and what we have with the problem set, okay, from page 318, and for what we have in the case of number 59, okay, so you have rational function, okay, and this is provided as f of x is equal to, and we have 4x minus 9 all over x squared minus 9. Okay, and if we look for the domain and the asymptotes, okay, so again we have the restriction that x squared minus 9 cannot be 0. Okay. So again we have this difference of squares to show up again. And again we have with the factors x plus and x minus 3. Neither of which can be 0. So for x plus 3, okay, we have the x cannot be -3. And for x minus 3, okay, we have the x cannot be equal to 3. And so we have for the domain, okay, we have two exclusions, okay, with negative and positive 3. First part, we have those values of x less than -3, and we have in the middle, okay, those values x between but not including -3 and +3. And then we have at the upper ends, we have those values of x which will be greater than 3. And looking at what we have for this function, okay, so you have 4x minus 9, okay, all over x squared minus 9. And if you notice, okay, we have x squared minus 9. Once again, we have x plus 3 and x minus 3. And neither x plus 3 nor x minus 3 will be a common factor with respect to the numerator. Okay, so in a sense, this ratio is already presented in simplest form. So in effect, we have both x plus 3 and x minus 3 remain. So both exclusions from the domain are going to be the vertical asymptotes. So now we're going to have two vertical asymptotes. So we're going to have x equal to -3. Also x equal to +3. And in the case of what we have in terms of any other asymptote, okay, so we got 4x minus 9 over x squared minus 9. And again, the 4x is a higher order term in the numerator. Okay, and that's going to be first order. In the denominator, we have x squared is the higher degree term. So we have n is at 1 and m is at 2. And in comparing, now we're going to have the n is less than m. And whenever the degree of the numerator is less than what is in the denominator, okay, there's going to be a horizontal asymptote, and y is automatically going to equal 0. And so we're going to have three asymptotes with two vertical and one horizontal. Okay. And in terms of the nature of the graph of this rational function, so we have three sections from the rational function, and you'll have again split up into separate sections. Okay, so now we got the horizontal asymptote at y is equal to 0. So y equals 0 is going to be the x-axis, and this, okay, there's only so much rich detail. Okay, but now x equals -3, x equals 3. Those are going to be the vertical asymptotes. Again, we have the horizontal asymptote, and we have for the sections in blue, okay, you have this curve in the lower left-hand section. You also have in the middle, okay, you have a bit of a zigzag pattern, okay, around the x and y axis, okay, and the origin. And we have to the extreme right, okay, and there's a slight appearance, okay, of the third section of this particular rational function. And again, now these vertical asymptotes are off limits. If you notice, we have this section of the rational function does intersect the horizontal asymptote. So just kind of mentioning again, we do have contact with the horizontal asymptote, and contact is a potentially possible occurrence, okay, whenever it comes to horizontal and slant asymptotes. But again, we're not going to have any contact or crossing when it comes to vertical asymptotes. So just wanted to restate this. All right, for what we have in the case of the next item, okay, we have for 60, and for this particular rational function, okay, it's not too much of a departure from number 59. And in this one, okay, we got f of x is equal to 5x minus 8 over x squared minus 4. Again, the restriction, we have x squared minus 4 cannot be 0. Okay, so like x squared minus 9, x squared minus 4 is a difference of squares. Again, the factors cannot be 0. And since the factors are distinct, okay, we're going to have two exclusions from the domain, and they're going to be additive inverses, just like what was the case with negative and positive 3. And this time for this particular function, okay, we have the domain to leave out negative and positive 2. Okay. So you have, again, three sections. You have those values less than the smaller exclusion. So you have values of x less than -2, We have those values x between but not including the smaller and larger exclusions, which we have with negative and positive 2. And then for the rest, you have those values greater than the higher exclusion. So we're looking at values of x greater than 2. And in terms of the vertical asymptote, okay, so you got 5x minus 8. We have all over x plus 2 times x minus 2. And again, this expression is already in simplest terms. So what this means, okay, is that we have x plus 2 and x minus 2 are going to stay. And we'll have another set of 2 vertical asymptotes. Okay, so both of these exclusions will be leading to the formation of the vertical asymptotes, which we're going to have at x equal to negative 2 and also x equal to positive 2. And for any other asymptotes, okay, so again, we now have the numerator. Higher order term is 5x. We have n equal to 1 in the denominator. Okay, we have the higher order term is at x squared, so m is equal to 2. And again, we have that n is less than m. And once again, we're going to have the horizontal asymptote to be y is equal to 0. So again, we have 3 asymptotes, 2 vertical and 1 horizontal. And the nature of the graph for this function will be the same as what we had in number 59. Okay, different points, different coordinates, but in terms of the general layout, okay, there'll be a lot of history repeating. So now looking at what we have, again, so you have 5x minus 8 over x squared minus 4. And again, you have the splitting up into 3 sections. And the middle section does cross and intersect and cross the horizontal asymptote, which we have at y is equal to 0. And again, you have separation created by the vertical asymptotes, which we now have with x equal to negative 2 and also x equal to 2. And again, have a lot of tangent activity, okay, to the extreme left and extreme right with regard to the horizontal asymptote y is equal to 0, which again is going to be the x-axis. All right. Now, in the case of what we have for the next items, okay, now we're going to have in number 70. Now this function is already going to be expressed in completely simplified terms. And for number 70, okay, we have the function, okay, so we got g of x is equal to x minus 3 all over x minus 1. Okay, just for the restriction, okay, the denominator cannot be 0. And we have the x cannot be 1. for the domain. Okay, had those values of x less than 1, and had those values of x, okay, greater than 1, okay, and again, g of x is already simplified. We're already in simplest terms. So that means that x minus 1 is not going to cancel out. So we want to have the excluded value of 1 to turn around and become the vertical asymptote. And looking at the degree comparison between the numerator and denominator. Okay, so you have x will be the higher order term in both the numerator and denominator. Okay, and again, the x terms are of first degree, so n is equal to 1, and we have the m is equal to 1, and so we have the n and m are equal to each other, and so we'll have a horizontal asymptote. And this is going to be at y is equal to the constant resulting from taking the ratio of the higher or highest degree terms in the numerator and denominator. So we got x over x, and this will go to 1. So here, vertical, we got x equal to 1, and for the horizontal, we have y is equal to 1. So you have two asymptotes in reference to our function g of x, or y, is equal to x minus 3 all over x minus 1. And just looking at the layout. Okay, so for these dark curves, okay, those are going to be the sections in reference to x minus 3 over x minus 1. And again, we have the asymptotes. We have x equal to 1, the vertical asymptote. And again, we have the y asymptote, and this is hovering above the x-axis. And again, these asymptotes do separate these particular sections that define what we have for our function f of x. All right. Now, with what we have also in simplified form, and we've got for the case in number 72, this time we have h of x, and that is equal to 2x minus 4 and we have all over x plus 3. And again, h of x is already in simplest terms. Okay. And concerning the domain, okay, so you have x plus 3. Cannot be 0, so we have that x cannot be negative 3. So we have for the domain, okay, we have those values of x less than negative 3, along with those values x which will be greater than negative 3. And again, since the ratio is in simplest terms, x plus 3 will not cancel out, and so this will signal that x equal to negative 3 is going to be the vertical asymptote. And for any other asymptote, again, we have coming down to comparing degrees of the numerator and denominator. All right, so we have we got 2x as a higher order term in the numerator. So this is our first degree, and in the denominator we have x, also first order. So you have, again, you have n and m will be of the same value. And we'll have, for the horizontal asymptote, it's going to be where we have y equal to the ratio where we have 2x divided by x, and 2x divided by x, okay, that is going to go to 2. And just looking at what we have here for this particular rational function, okay, so we have, in the case of 2x minus 4 all over x plus 3. Okay, kind of like the graph earlier, you have split up into two separate regions, and you have running to the left and up and down to the right and below, okay, the kind of plus formation created by the vertical and horizontal asymptotes. And again, we have for the vertical asymptote, again, we have to the left of the y-axis at x equal to -3. And for what we have in the case of the horizontal asymptote, you have hovering above the x-axis. Okay, so we have y is equal to 2. And again, these formations, okay, do kind of contain, okay, the sections that are formed by our given rational function, again, which we had at 2x minus 4 all over x plus 3. All right, now, and just kind of, yes.
So this one, I was super confused because in the textbook, it wanted you to graph this equation.
Right.
And so I was trying to find the y-intercept and the x-intercept.
Mm-hmm.
And when I found the x-intercept, it looked like the graph couldn't even possibly go through it.
Okay, now for
and go through the y-intercept at the same time.
Okay, now for let's see. Now for the y-intercept. Okay, now the y-intercept is going to be non-integer amount. Okay, like if you have, like, for the y-intercept, say if you plugged in 0 for x, you have like 0 minus 4 is -4, and you got 0 plus 3 is 3. So the y-intercept would be like at 0, -4/3. Okay, so this would be just underneath y is equal to -1. So you have like this portion, y-intercept would be right here. So you have like y is equal to -4/3. And for the x-intercept, now there's going to be only one of these. And if I set y to 0, okay, have like, okay, so you have like multiplying both sides by x plus 3, you would have like 0 is equal to 2x minus 4. Okay, so 2 times y minus 4 is equal to 0, and you have like 2x equal to 4, and you have x equal to 2, and x equals 2. Okay, that would be your x-intercept. And in terms of any other points, okay, you'd be looking at selecting, say, like random values of x and y, to get the formation of points. And it'll be with a lot of these rational functions that if you get like the x-intercept and y-intercept, it might be located at one part or one section of both regions that are formed by the rational function.
So I did the x-intercept incorrectly, and that's why it didn't.
Oh, okay.
But
yeah.
I had another question. So, like, if let's say I had done it correctly and I had found that bottom curve.
How
do I know where the other curve is? Like, is it just going to be straight across like it is on there always, or could it be to the left, or could it be above it?
Okay. What we have in this particular case, all right. Now, it could say that you could kind of say that in a sense. You could almost do it like in the case of counting squares. Okay, and kind of like mirroring across. Okay, so you have like, let's say you like to get to the x-intercept, so you have like where you have the asymptotes to intersect. So you have like going down 2 and to the right 1, 2, 3, 4, 5 places. And if I were to start here and go up 2 and then to the left 1, 2, 3, 4, 5, I have like the mirroring across where the asymptotes will intersect. Okay, so you have like 2, 0, 2, 0 here. Okay, so you got like 2 down, 5 to the right. But if I go like just like the inverting, so you have like going 2 up and 5 to the left, and see that is going to be, so you had x equal to -2, 5 to the left, and so that is going to be, let's see, you had y was equal to 2, x is equal to -3. Okay, so if we go up to 2, so we have, in this particular case, let me hold on, let's see, y equal to 2. Okay, so I have going up 2 and out to the left 5 places, just kind of mirror across, and that should be, see, your y value is going to be at 4 and x was at -3, so I think that's going to be -8, 4. So you have this, for instance, so I can check here. So if x is -8, yeah, so 2 times -8 minus 4 is -20. -8 plus 3 is -5. Yeah, and your y value is going to come out to 4. It's going to be like a bit of a reflection about where the horizontal and vertical asymptotes will intersect. That's one way that you can look at it, kind of like counting the grids or the patterns.
Right, thank you.
Okay, now for what we have now for the case in number 86, and this one is going to be a bit of a departure from the other functions we've dealt with. Not too drastic, but just little different. Okay, and in case this item, we have for 86, now we got u of x is equal to -3x squared. And we have all over x squared plus 1. And so we're back with that x squared plus 1, and it will be a bit of history to repeat, say, from the first example. Again, you're going to end up separating the x squared apart from the constant. So you have the x squared cannot be -1. And again, we have with the square root property, okay, again, the exclusions will be complex numbers, so there's no real value excluded from the domain. And so what that means, okay, again, is that we're back to where the domain is going to be the set of all real numbers. And also with no real values excluded, there's nothing that can become a whole or a vertical asymptote. And in terms of any possible existence of an asymptote, okay, so we have in the case of the numerator and denominator, okay, the degrees will each be at 2. And here we have that n is equal to m, and we're going to have resulting horizontal asymptote and we'll be taking the ratio of the higher degree terms. Again, so we're going to have a horizontal asymptote. So you have y is equal to negative 3x squared over x squared. And so we're going to have that y is equal to negative 3. And in terms of the visual layout, for this one, okay, this is going to be kind of and kind of an interesting layout. Okay, so we have for this graph, okay, you have a bit of a wave here with the rational function graph, and if you notice at the base, okay, you have running tangent to the left and to the right, and barely across, okay, or barely above the horizontal asymptote, which we have a y is equal to negative 3, and this one, okay, has looks almost like a normal distribution curve, or what they call a bell curve. You have symmetry on both sides, both halves mirroring each other, okay, about the y-axis. And again, okay, this will be the layout here, and again we have no vertical asymptote, just a horizontal asymptote, where we have y is equal to negative 3. Now, for what we have in the case of number 90, and we have for this particular rational function, and this is going to be its own kind of rational function. And here, okay, we're going to have f of x is equal to 4x to the fourth, and we have all over x squared plus 8 . Okay, so again, we have a sum of squares in the denominator. And you probably know, okay, about what direction this is going to be headed, because again, we're not dealing with complex numbers. Okay, so you have x squared cannot be negative 8. Okay, so we go from x squared to x. Okay, so x cannot be plus or minus the square root of negative 8. All right, and we're already going to have complex numbers. So there'll be no real exclusions, but just kind of going back. Again, you got the square root of negative 8. And this will be square root of 8 times I, and reducing the radical. So again, the highest perfect square divisible into 8 is going to be at 4. And square root of 8, we have square root of 4 times the square root of 2. Square root of 4 is 2. We have times the square root of 2 times I. Okay, so if we had to state just what the exclusions would be, we would have them only from the complex number system. Okay, and so again, so you have no real values excluded. So that means that the domain, okay, this is just going to roam free. Okay, we have the set of all real numbers. Okay, you have another case of where there's no whole or vertical asymptotes. and comparing the degrees. Okay, so the numerator degree is going to be at 4, and the denominator degree we have defined by the higher order term at x squared, so m is equal to 2. And for what we have here is that this is going to be our only case out of the prior problems and examples where you're going to have that the degree, the numerator, is going to be greater than the degree of the denominator by more than 1 degree. And with the difference being more than 1. Okay, this is going to signify that not only will there be no vertical asymptote, but there will also be no horizontal or slant asymptote. And just kind of picturing what we have with this particular rational function. Okay. And the graphic, it can be somewhat a little bit deceiving. Okay, now I got y is equal to 4x to the 4th over x squared plus 8. Now we have what appears to be something like a parabola that is opening up, but we're not dealing with a quadratic function, at least not in the strictest of terms. And okay, so you got the base. Okay, so you have right at, y is equal to 0, and one might be tempted to say that looking at this, there will be a horizontal asymptote at y is equal to 0, but for the extreme left and the extreme right, you should have the graph sections to be running tangent to y is equal to 0. But once you start to venture out to the left and to the right, there's no horizontal containment. And for what we have in the case of what we have running vertically, okay, now this is where it can look a little bit deceiving too, okay, because it looks like, just on the basis of what I have graphed, it looks like it's somewhere between x equals -3 and x is equal to +3. But the thing about this is that you're also going to have expanding both horizontally and vertically. And in the case of opening upward, okay, you're looking at this drift to ever so slowly be going out to -infinity on the left hand side and out to +infinity on the other. So there's no vertical or horizontal containment to where we can say that we have any asymptotes. Right, so this is our case where we don't have any vertical, horizontal, or slant asymptotes to exist. Now, looking for domain and asymptotes. And tell you what, for the next few moments, okay, tell you what, let's see what we get for the domain and asymptotes. Now we'll say that we have here for the domain and the asymptotes. And we'll say that we have in this instance, okay, so we got for, let's say for r of x, and we'll say we have x squared plus plus 5x plus 3. And we'll say we have all over x plus 1. So let's see what we get for the domain and the asymptotes. R of x is equal to x squared plus 5x plus 3 all over x plus 1. Okay, if we go ahead and look at this rational function, okay, so we have with x squared plus 5x plus 3 all over x plus 1. Okay, again, for the domain, okay, we had the restriction to be the x plus 1 cannot be equal to 0. Okay, so we have the x cannot be equal to negative 1. So we have for the domain, okay, we have those values x such that x is less than negative 1. We also have those values of x, okay, such that x is greater than negative 1. Okay, and we have for this particular ratio, okay, this is already in simplest form. And so we're going to have a vertical asymptote. Okay, the ratio is already in simplest form. X plus 1 is not going to cancel out. So there's going to be a vertical asymptote with x equal to negative 1. Now, for the rational function, in terms of finding out if we have any other type of asymptote, okay, again, we have from the numerator, okay, we have the highest degree term is x squared. From the denominator, okay, the term that defines the degree is going to be x, which is going to be of first order. And so we're going to have that n is equal to 2, n is equal to 1. And we'll have that n is greater than m by 1 degree. Okay, so in this case, the other asymptote is going to be 1 that is a slant asymptote. Okay. And you can arrive at the slant asymptote by taking polynomial division. Okay, and you can go either of two ways this time around. Okay, now before, with the other slant asymptote examples, okay, I had to determine what it was on the basis of taking long division. And that's because the divisor was consisting of an x squared term, but now we've got the divisor to be first order. So I can put this setup in terms of synthetic division. Okay, so we got x plus 1 is equal to 0. And we have x equal to negative 1. So I can say that by synthetic division, let's just refashion this. Let's have x at negative 1. And for the coefficients of the dividends, I have 1 for x squared, 5 for x, and 3 for the constant. And so we got here, so bring down 1, negative 1 times 1 is negative 1, 5 plus negative 1 is 4, negative 1 times 4 is negative 4, and 3 plus 4 is negative 1. And again, I don't have any particular interest in the remainder, which we do have at negative 1. What I do have interest in, okay, is going to be the quotient, okay, and this will be signaled by the 1 and the 4 in front of it. So we have with the quotients, okay, again, the 1 at the front initially referenced 1x squared, but in the quotient, it's just going to reference x, and the 4 that follows, okay, that's going to be the closeout for the quotient, okay, so in this particular case, we got the quotient at x plus 4. And so we're going to have a slant asymptote. Whereupon we're going to have that y is equal to x plus 4. All right. Okay, so we have two asymptotes, one vertical at x equal to -1, and we're going to have a slant asymptote at y is equal to x plus 4. All right. And now we've been looking at alternating between factoring, multiplying, and dividing polynomials, and we've looked at combining terms, and also been looking at solving equations, some of them with polynomials, some with rational functions, and also like going back to the very first chapter, in chapter R, we looked at combining terms, some integers, some non-integers, some variable terms, some constants, and we crossed over to equations, and ultimately we had crossover to inequalities. And for what we have in the next portion, we're going to have also in chapter 2, we're going to have inequality statements. And for what we have over in section 2.6, we'll have what would be regarded as polynomial inequalities. And we'll give you just kind of an introduction to this. Okay. So if I were to determine the values of x, for the following. Now I'm just going to use 3 cases here, working with the same polynomial function. Okay, we'll say we have x squared minus 4 is equal to 0, and where inequalities come in, okay, this be like your less than, greater than, less than or equal to, greater than or equal to statements. And we'll say that we have looking for the values of x such that x squared minus 4 is less than 0, and it's also where we have x squared minus 4 is greater than or equal to 0. Okay, so we have in the first part, okay, so we got x squared minus 4 is equal to 0. So again, we have a difference of squares, and we've been factoring out intermittently x squared minus 9 and x squared minus 4. Again, so if x squared minus 4 is equal to 0, we're going to have the values that will make this statement true. We have from x plus 2 is equal to 0. Then we have the x is equal to -2. And for x minus 2 equal to 0, then we have the x is equal to 2. Okay, so you have x equal to negative and positive 2. Right. Now, for what we have in the case of the second and third items, okay, and give you just a bit of a backdrop here. Okay, now we got again, so we have x squared minus 4 is equal to 0. Now for the setup in the case of number 2 and number 3. Now we got our function f of x. Is equal to x squared minus 4. And now for the zeros of f of x, in other words, what we just solved, okay, whenever x squared minus 4 was equal to 0, we had the zeros at x equal to negative 2 and x equal to positive 2. And where the inequalities are going to come in, what I'm going to do here is I'm going to set up a table. Okay, and at the top, okay, so we have interval sections. Okay, and we'll kind of run the spread here. Let's see if I can. Yeah. I'll just widen this. Okay, so we have for the interval sections. Okay, so we'll be working around negative and positive 2. So think of it kind of like if you had the domain to be exclusive of negative and positive 2. So we just have like at the lower end we have those values of x less than negative 2. And then you have those values of x between but not including negative and positive 2. And we have for the rest, we have those values of x, okay, which will be greater than 2. And what we're going to do, okay, so we're going to test each of these interval subsections. Okay, what I mean by this, okay, with test value x, I'm going to select some values that could be at random, but you want the value of whatever number you choose. It could be negative, say like anything less than negative 2, it could be negative 100, it could be negative 1,000,000. But I like to keep the numbers kind of as small and the absolute value as much as possible. So if you got like select a number that is less than negative 2, I'll go with negative 4. And between negative and positive 2, now if I want to go with integers, I can pick negative 1, 0, or 1. Those are the only 3 possible integers I can choose from. If you go with negative 1, that's fine, or positive 1, that's okay, but I'm going to go with 0 in this case. And then we have anything that is greater than 2, I can select, and I'll just go with the number 3 in this case. All right. Now, in terms of what we have after selecting, we'll be looking at finding out what the value of the function is going to be for each chosen value in x. So right now I have f of x equals x squared minus 4. And just separate in case I got f of x is equal to x squared minus 4. And I want to find out what the value of f of x is going to be for each of the selected tested values, okay, for the inputs. Okay, so we got with negative 4. So if I go with f of negative 4, okay, so that's going to be the square of negative 4 minus 4, and the square of negative 4. Negative 4 times negative 4 is going to be 16. And 16 minus 4, okay, that's going to come out to a positive 12. Now if I choose 0 for x, okay, so the value of the function, so for f of 0, we have 0 squared minus 4. Again, 0 squared is 0, and 0 minus 4, okay, this is going to come out to a negative 4. And for f of 3, so I'm looking at 3 squared, x squared is 3 squared, and we have minus 4. 3 squared is 9, and 9 minus 4 is going to come out to a positive 5. Then we'll have next, okay, for the sine of f of x. I'm just going to partition these sections. Okay, so for the sine of f of x, okay, if you notice again, what I have in red, okay, so I had selected a value less than negative 2, and with negative 4 chosen, the output was positive 12. And this is a sample that anything in the input that you choose that is less than negative 2, your function value or output is going to be positive. So in this case, you would have f of x to be greater than 0. Okay, now anything we select for the input, okay, that is greater than negative 2 but less than 2, like 0 being a case, the output is going to be negative, like in the case f of 0 led to negative 4. Okay, so output is going to be negative. Okay, so you have f of x is going to be less than 0, and then anything we choose for x that is higher than 2, okay, 3 is an instance, the output, like your y value, is going to be positive, like positive 5 being such a case. And so we have the f of x is greater than 0. Okay, now for the solutions, okay, to the inequalities, okay, so again for second problem, okay, we had that x squared minus 4 is less than 0, and this, okay, and we got f of x equal to x squared minus 4, and so this statement is going to be representing, okay, where we had that f of x is less than 0. Okay, so if you notice, you have f of x is less than 0 in the middle section, and what you have at the top, okay, just what set of values x we're going to have. So just looking at the top row, we're going to have for the solution, for a solution. Okay, so you're looking at the top. Okay, so you have less than 0. So we're going to have those values of x such that negative 2 is less than x, in turn is less than 2. And for what we have in the case of x squared minus 4 is greater than or equal to 0, okay. So we'll be making reference this time to f of x is greater than or equal to 0. Okay. And so for what we're going to be referencing, okay, now you've got f of x is greater than or equal to 0 is going to be in the same direction as f of x is greater than 0. So for the limits of interest, okay, we're involving these particular portions. Now, for the solution, okay, so we are involving negative infinity and negative 2, as well as 2 and infinity from the top rows, okay, where we have in correspondence, okay, to where we have in the same column as where f of x is greater than 0 is located. Okay, and in terms of the closeout, okay, so infinities are boundless, so they're going to remain in parentheses. And had I been presented the problem x squared minus 4 is greater than 0, I would also have parentheses around negative and positive 2. But those values create the equal to 0 portion. So with negative and positive 2, instead of having parentheses to contain them, we will have brackets to use as enclosures.